Okay. So, thanks to the organizers of SMC UT Austin and for giving me this opportunity. So, my topic in this summer mini course is algebraic topology, basic notions of algebraic topology, and in this course I will cover two important notions that are. So one is covering spaces, and another one is deformation retracts. Okay, and these two objects will be needed to compute fundamental groups that will be discussed today. Fundamental groups of some spaces, and hopefully we are looking on some fundamental groups having non-trivial fundamental groups. Okay, so let me start. So okay, so first of all, I would like to just give some examples. That is, suppose you take. So what is the motivation behind defining fundamental groups is that because whenever we are looking at topological spaces, we are going to distinguish two topological spaces by means of their properties that they are enjoy. Okay, so that means so our basic motive is that to make topological spaces homeomorphic to each other. Okay, that means you need to construct some map between two topological spaces, and that will be a bijective map, and that needs to be continuous, having continuous inverse. Okay, but sometimes constructing continuous maps having continuous inverse may be a cumbersome job. Okay, so what we are doing is that we are doing the in contrast to this. So what we are looking at, so rather we need to find out some properties which one space will enjoy, but the another one will not. And with this one, you can say that these two spaces will not be homeomorphic, right? And these properties are commonly known as, these are topological invariants, right? Topological invariance. Okay. Suppose you look at the two familiar spaces. That means suppose you take the real line that is equipped with the usual topology, and another one is unit circle. Okay. Now these two spaces, this is a very easy exercise that these are not homeomorphic, right? These are not homeomorphic. Why it is so? Because basically, if you remove one point from each space, then this space, suppose you are omitting one point here, suppose let us call it 0, and you are deleting this point here and delete the point, suppose here. Okay, but still this S1 is connected, but this will not. This will not be connected, right? So
Excuse me, sorry. Did you want to record this or?
yes,
Okay.
yeah. Actually, if you remove this 0, so that will be disconnected, right? So, but still S1 is connected, right? So, yeah, great. Now, now look at another two familiar spaces that suppose it is coming here. Suppose we look at R2 and R3. Okay. Now, what we can do now in R2 or R3, if you remove some point, you cannot use the same argument that has been used in the previous example, right? So, because suppose you remove one point here, okay, so that means you are taking R2 minus this, and you are going to remove one point here. For convenience, let us make it 0, 0, 0. Okay. Now, R2 minus 0 still it is connected, right? Similarly, the case is true for R3 also, right? So R3 minus 0 it is still connected. Actually, they are part connected, so you can say that they are connected. So we cannot use the same argument that has been used in the previous example here to make so the spaces that they are distinct topologically, right? Okay. Because but there is a nice kind of notion that has been that can be taken up here. That is, suppose you delete this 0 and you are looking at some closed path around this 0. Okay. And you are doing the same pathology in this space also. Okay. But still, suppose let us, yeah. So this is R3 minus 0, 0, 0, and this is R2 minus this. Now you have some kind of problem that will be rising here, that this path cannot be deformed to a point continuously because of this hole, right? Whether in R3 minus, so this space, this path can be easily shrunk to a point continuously, right? So there is a notion that that is coming out here, that this path cannot be deformed continuously in R2 minus 0, but the corresponding path, closed path, it can be deformed to a point continuously, right? Yeah. Good. So again, let's come back to the space. S1 again, okay? And now I'm going to take a very familiar space, Riemann sphere, that means it is S2, right? Yeah, great. Now here, So it is well known to all of you that this S1 is not homeomorphic with S2, right? Suppose you take out one point from S1, sorry, if you take out 2 points from S1, and if you take out 2 points from S2, then you can make some distinction here, distinction from S1 and S2. That is, this space it will get disconnected, but still S2 will be connected, right? And if you take any path, suppose you are deleting 2 points, suppose one is North Pole, another one is South Pole, but still if you take any closed path here, this can be deformed to a point continuously, right? Very good. Now there are such spaces. So that means in basic general topology, so far we have studied. So the topological invariants will not make use to make a distinction between these two spaces, right? These familiar spaces at least. Okay. And there are more spaces that we are going to form. That is, another one is a very well-known surface, which is torus. So this is a okay, great, and making a connected sum with the torus with itself, we can make double torus. Just take out, so just considering two torus and then take out a open disk from that two torus and then let them do. Okay, so then you will find out this space. So this is a double torus. I am just going to denote it by this, with this notation. Yeah, great. Okay. So the unavailability of suitable topological invariance as of now that we have studied will motivate us to introduce a very natural property which we have been informed a little bit whenever we are studying complex analysis, right? We have already seen some domains which are called simply connected domains, right? So which informally means that it is a space. So it is a space where every closed path in X can be deformed, shrunk to a point continuously in that space. Okay. And this has the power to distinguish that we have already seen that R2 and R3, right? We have already cited that example. And it will also distinguish S2 and the torus. Okay. But this fails to distinguish this torus and double torus. We will see later. And along this line, so I'm going to define what does it. So I'm going to associate for any. So we are trying to associate for every topological space a group. Okay. So I'm going to transform the problem of topology to a problem of algebra, right? So we're trying to associate for every topological space a group which is known as fundamental group. Correct. And using this notion, you can easily define simply connectedness. Okay. So, which is enjoyed by R3, right? R3 minus 0, 0, 0, right? But it has not been enjoyed by S1 minus 0, 0. I'm sorry, R2 minus 0, 0. Yeah. Okay. Great. So to define this group, we need to focus on some ideas, basic ideas. That what does it mean by? So what does it mean by homotopy of paths, right? So suppose we consider a space X and spaces. Suppose we consider two spaces X and Y, and let us take two continuous maps F and G from X to Y. Okay. Then what we are doing that. So this F, so this is defined to be homotopy to the map G if one can find out a continuous map. That means suppose let us draw. So this is X cross 0, 1. I'm taking the unit interval here, closed unit interval. And this is your, suppose, let us take the Y here. So the maps are, so one is F, okay, and another one is Z. And I'm going to define that F is homotopic to G if you can find out a map from X cross this interval, suppose H, such that if you look at this base, that means this will be taken to this F. So this part will be there, and this part will be mapped to here. Okay, so that means you can write down it in terms of coordinates, that is Hx at 0. So this is Fx, and Hx at 1, it is Zx. That means at 0th level, it will be mapped to F, and at 1th level, it will be mapped to G. Okay. And during that deformation, so that means suppose you are taking some, so this is suppose at T, right? So that means we are getting some map here, right? So this is nothing but this is HT. That means whenever you are constructing a map H from X cross 0, 1 to Y, actually you are getting, so we are getting a family of continuous maps HT, right? So that could be defined in this way. So this is HXT, right? Where at 0th time it is F, and at 1th time it is Z. So F will be deformed continuously to G. So that is that. So if F is homotopic to G, we denote it by F equivalent to G. Okay, great. And this H is called, where H is called the homotopy. Okay. Great. Now, as we have already witnessed some examples that some closed path, so we are just closely looking at those paths which are deforming to a point. So that means, so path is a continuous map. So I'm going to just announce this one, that if F is homotopic to a point, or we can say that homotopic to a constant map. Okay, then F is called null homotopic. Okay, great. Now let us move forward for paths having endpoints A and B. Okay, so that means suppose we take, so a path means, so this is a continuous map from closed unit interval to X. And this is a very nice kind of space because it is convex, it is compact, right? And it is connected. So we are defining that. So gamma is a path, means it is a continuous map, but we are looking at some paths which having endpoints A and B. So that means, so a continuous map, so that comma 0 is A, comma 1 is B. So the initial point is A and the end point is B. Okay, great. So now let us take two paths. So let take here. So this is your X, and let us take two paths. Suppose this is your A and this is your B, and this is your F, this is your gamma, and this is your sigma. So I'm taking two paths, gamma and sigma. So using this gamma 0 is A and gamma 1 B, so you are having some orientation also. It is inbuilt here, right? Okay, so now this gamma, so two paths let us draw here. Yeah. So this is, so let I is closed interval 0, 1. So now I'm taking I cross I, right? As per the definition of two maps are homotopy. You are going to have some homotopy which is from X cross 0, 0, 1 closed interval to Y. So now we are considering paths, that means these are continuous maps from closed interval 0, 1 to X. So that means we need to have some homotopy idea from 0, 1 closed interval cross 0, 1 closed interval to X, right? So that is why we are taking I cross I. So that means it is 0, 0, this is 1, 0, this is 0, 1, and this is 1, 1, right? Great. So we need to set up a map here. Suppose let us call it F. So two paths, gamma and sigma, are said to be path homotopic. We are denoting it by this symbol, path homotopy. Right? If there exists a continuous map as before, from I cross I to X, such that so whatever has been defined earlier, that will be taken up here. That means you are taking the so this side. So this side will be mapped to gamma, and if you are at one level, then this will be mapped to sigma. Okay, and for other line segments joining these two sides, yeah, so that will be mapped to some paths joining A and B. Okay, yeah, great. So that means, as has been seen before, so we are getting a family of paths, right, which are FT, defined by where FT of S is f of S comma T, where at the 0th level it will be gamma, and at the 1th level it will be sigma. And during that deformation, the endpoints will not be changed, right? So that means, and f 0 comma t must be A, f1 comma t must be b. Okay. Oh, someone is asking me that did you want to record this? Yes, but how can I? It's possible to record. Okay. So may I start recording? So I need to, okay, ask the host to give you permission. Yeah. So I think I can record from tomorrow. Okay. Okay. Great. Okay. So now whenever we are looking at the okay, so this F will be called path homotopy. Great. Good. So that means uh, yeah. So that means if you take a class of continuous maps from X to Y, then you can define a relation there. So that means suppose you can define this homotopic relation being homotopic. And likewise, for paths having two endpoints, A and B, you can take relation being path homotopic, right? On a class of paths from A to B in X. Okay. Now I am going to give you some exercises. So this will be left as an exercise. You need to check first one that these two relations are reflexive, it is symmetric, and it is transitive. Okay. Now, in the transitive case, there is a very nice, you need to look after this transitivity because you need to consider two homotopies, right? So that means, so suppose you are taking, so I'm going to just discuss on this one only. So let us take three continuous maps. Suppose one is F, G, and H. Assuming that F is homotopic to G and G is homotopic to H, and you are going to claim that F would be homotopic to H. So that is your claim. And this is obvious because of this fact. Let me just for here. Yeah. So suppose it is your X and you are taking three maps. Suppose F, G, and H. Okay. Yeah. So F is homotopic to G. So that means there is a homotopy. Let us call it H. So there exists a continuous map from H from X cross I to Y, such that at the 0th level it is F, right? And at the 1th level it is Z. Great. Likewise, you can have another map from X cross I to Y, another continuous map, such that at the 0th level you will get G, and at the 1th level you will get H. Okay. Now you need to make some kind of gluing here, right? That means we are taking them together. But how can I? Because of this fact, that is, suppose you are at the 0th level. So this is your X, and let it be at the 1th level. So this is your X cross I. Okay. So this is at 0th level, and this is at 1th level. Now I am going to take these two homotopy together. So we are going to divide this cylinder, general cylinder, right? So in two parts. Yeah. That means one half will be occupied by these two homotopy, these two continuous maps. Suppose let us make it half. So that means, and this part will be occupied by, yeah, this one. Just by using pasting lemma, you can always construct this kind of map by taking them together, by making a partition of closed interval 0, 1 into two parts, into two equal parts. That means, so we define, so this is a common technique that we are adopting in future also. So define some map F from this to Y by this rule, that is fxt must be H. This is H, right? This is H. So Hx, let us make it 2 into T for this part. Okay, that means from 0th level to half level. So you are taking this map. Okay, and after that, you will take this homotopy, that is from half level to 1th level. Okay, And by testing lemma, you can say that this f, it should be a continuous map on x cross I to y, right? Satisfying that, so if you are looking at this f from the diagram, it is clear that this will be mapped to f. So this is your f, capital F, and the 1th level will be mapped to h, right? If we just execute some computations here, so fx0, so that will be hx0, right? So that means it is fx. And if you take the 1th level, so that would be gx1, right? So this is hx, great. Looks to x. So that means f is a homotopy in between f and h. So that means, so hence f is homotopy to h. So transitivity holds good. Great. So that means these two relations, so if you take the being homotopy relation, so that will be an equivalence relation. If you take the path homotopy also, that will be an equivalence relation. Great. So you can make a theorem here. So these two relations are equivalence relations on the respective classes of maps. Okay. Okay, great. Now, there is another nice choice of homotopy that we can use in many cases, which is a very, suppose I'm just exploring some examples, at least one example. So let us take that one, that suppose we are taking punctured plane, although it is not needed here, but still just take this one and take two paths. One is the semicircle, unit semicircle, that is the upper semicircle, and another one is an ellipse, the upper part of that ellipse. Okay, great. So these are two paths having same terminal points, right? Now what you can do, so suppose this is, okay, so what you can make a choice of homotopy here, that we can choose, suppose you take one point here, let us denote it by, it is gamma and it is sigma, okay, and one point here, right? So you can draw the line segment connecting these 2 points, and you can do this all over this one, yeah, okay. So that means these 2 paths are homotopy, and during the homotopy, so these two terminal points will not be changed, right? So if you look at the, so that means, so this is the homotopy, suppose it is HST, so you can take it as 1 minus T comma S plus T sigma S, right? You are just taking the line segment, joining the points, right? So in this way, you can say that these two paths are homotopy, and this is a path homotopy, right? Great. But this kind of homotopy is called here, it is called straight line homotopy. Okay. Straight line homotopy. Great. So generally speaking, So generally speaking, what we are assuming the space to be, so if we consider in general a topological vector space, right, X and a subspace of X, so be a non-trivial subspace, right? Yeah. Then, yeah. So then two paths, suppose gamma and sigma, with same terminal points in A. So are said to be, so gamma and sigma having same terminal points, okay, in A. That means we are defining the paths in A. A is a subspace of X, right? So X, you can draw lines, right? So therefore, you can talk about straight lines. So these two paths having same terminal points, so these are said to be straight line homotopic, right? In A, if there exists a continuous map H from I cross I to A given by that we have used here, we are adopting the same kind of map here. So HS comma T, so that is in the line segment connecting the points gamma S and sigma S. For all S comma T belongs to I. Okay. Denoting it by, so we denote it by using this notation. Whenever we are talking about straight line homotopy, we are denoting it by just putting an L here. Okay. And whenever you are talking about paths having same terminal points, so if you can find out some straight line homotopy, so that means so it is essentially the path homotopy, right? So therefore, so this implies that they are path homotopy. So this is a very easy fact. Okay. Okay, great. You can also define straight line homotopy. Suppose you take any space X, okay, any space, but you need to take the codomain space as being a topological vector space. Okay, then you can easily define straight line homotopy between two continuous maps. Then straight line homotopy between two continuous maps can be defined. Okay, great. Okay. Now I'm going to just give you some exercises which will be needed in our future discussions. So let us, so these are left as an exercise, but we will need these properties in future. Okay. So first one is a very important one. That means if you take two continuous maps, okay, if you take three spaces, suppose X, Y, and Z, okay, and we're assuming that F and F dash be two continuous maps from X to Y, and these are, so F is homotopy to F dash. Okay. Homotopic 2. And let us take another two maps, G and G dash. They are also homotopic to each other. Then you need to show that G compose F is homotopic to G dash compose F dash. Okay. Yeah, check. What would be the homotopy between X plus Y to Z? Okay. Okay. Now some simple facts that if we denote this box xy by this the set of, as we have seen that the relation of being homotopic is an equivalence relation, so you can partition a class of continuous maps from X to Y in distinct equivalence classes of continuous maps, right? So therefore this is a set of homotopy classes. Homotopy classes of maps of X into Y. Okay. Now, if you consider Y to be just closed unit interval, then you can check that this is nothing but this will be a singleton. Check. Okay. Whereas instead of taking Y to be 0, 1, let us take X to be 0, 1. Now, if we let X to be closed interval 0, 1 and Y is a path connected space, okay, then you will get that set again a singleton. Okay. Good. Okay. Now let us move forward to define what do you mean by contractible spaces. That means so if you look at the example, now we look at the following example. That means suppose you take the closed interval 0, 1. Okay. Then in this interval, this is a closed interval 0, 1. So suppose you take any X here, then this can be moved to the point half, right? By choosing a line segment. You just need to have some line segment connecting this X and half. You can always draw this kind of line segment here because it is a convex space, right? But what does it say is that, so this says that, so this depicts the fact that if you take the identity map from I to I, so this is homotopic to a constant map, right? Constant map at half. Okay, because you can take any X to half by means of a line segment, right? So this kind of spaces, are known as contractible spaces. That means where the identity map is null homotopic. Okay? So we can take up this definition here. So space X is defined to be contractible if Ix is non-homotopy. So in future, we will come across some contractible spaces. Okay. And at this moment, we have one, which is closed interval 0, 1, but you can also take that R, real line. Okay. So for example, so for some ready examples, so you will have this R. Okay. So this is a contractible space. Just using the same arguments that have been used above. Okay. Great. Now let us yeah, okay. And so let us list some notes. So note 1. So suppose you take X to be a contractible space. Okay. So what kind of benefit you will have if you are having some contractible space? Now you take any, so let us consider any space. Okay. Y. And from Y to X, we are taking two maps. Suppose one is F, another one is G. Okay. Two continuous maps. Again. Great. Now, these two maps will be homotopic. Why? Because of you are having this benefit of having contractible spaces. That means the identity map will be null homotopic. That means, so since I, suppose Ix, so it is null homotopic. That means, suppose it is homotopic to the constant map at x0, x0. Okay. Then, by the use of the exercises that I have given earlier, this implies that Ix compose F. So this is homotopic to x0 compose F. But since x0 is a constant map, so then what will happen? These two are homotopic, right? And again, by the use of the same arguments used here, this is homotopic to Ix compose G. Correct. Therefore, so from this one, you will have F, right? And since the relation of being homotopic is a transitive relation, so you can say that this is G. So therefore, this is homotopic to x0, this, homotopic to this, right? So by using transitivity, so F will be homotopic to G, right? So that means if you have some contractible space, then any two maps, any two continuous maps from any space Y to X will be homotopic. Okay. Correct. And using this fact, you can say that Yeah. Okay. So yes. So then, so suppose you take a contractible space, and let us take a path from x0 to x1. Let us call it gamma, and another path from x1 to x2. Let us call it sigma. Okay. Then what can be said here? So that means, so what is x1? What is x1? Since x is contractible, so the identity map will be homotopic to uh, yes, this one, right? Sorry, yeah. And then you can define some h here from I to x, so that, so what is h? So h of t, so it is gamma 2t. That means we are dividing that closed interval into two equal parts, and this is your sigma 2t minus 1. So you are using the same technique whenever we want to use pasting lemma for these kind of situations. Okay. Then this h, so this is a path from x0 to x2, right? So this says that, that means, so what does it say? That x became path connected. Okay. So that means any contractible space is path connected. Okay. And you have lots of examples that the converse will not true. That is problem here. So does the converse hold? Okay. So justify your answer. Okay, great. Another note. So not only the real line, you will have lots of spaces that are contractible. Which are those? If you take any Rn, so these are all contractible spaces. Why? Because of convexity, right? The same situation will happen for Dn, closed unit spheres. So these are all contractible spaces. Okay. And generally, you can, if you take any subset, any subspace in Rn, any a convex set, okay, then it must be contractible. So generally it is true. So there are many examples of contractible spaces. Okay. We can also define this contractibility of some space using deformation retract. Okay. But that will be come up later. Okay. So now what you do? So now we take, so let us take, consider a space X. Okay. And then suppose this is a path from x0 to x1, and also we are defining another path from x1 to x2. Okay, so let us call it sigma. Then using these two paths, where you are assuming something, that means the end point of gamma will be the starting point of sigma. So here, what is that? This is gamma 1 and this is your sigma 0, right? So you are assuming something here, that the end point of gamma should be the starting point of sigma. Okay. Then using Pesting lemma, you can define a path from x0 to x2. So we can define a path capital gamma from x0 to x2, right? Great. Now, suppose you have, so let us have two space. Suppose we take two paths from x0 to x1. Okay, suppose we take, so one is gamma, another one is gamma dashed. Okay, from x0 to x1. Similarly, we are taking a path from this x1 to x2. Two paths from x1 to x2. One has been defined as sigma, another one is sigma dashed. And we are assuming that this gamma is path homotopic to gamma dashed and sigma is path homotopic to sigma dashed. Okay. So that means you can define two path homotopy. So suppose F be a path homotopy between gamma and gamma dashed, and G be a path homotopy between sigma and sigma dashed, right? Great. That means you are constructing some map from the unit square, closed unit square, I cross I to X, such that at the 0th level it will be gamma, at the 1th level it will be gamma dashed. Okay. And the same thing will happen for sigma and sigma dashed. Okay. So that means we are considering two continuous maps. So one is F, another one is G. Right. So let us draw again. So what we do here, we have we are adopting the same idea that we are dividing this square into two equal parts. Okay. So that means, so let us this one, and this is by introducing half. Okay. 0, 0, 1, 0, 1, 1, and 0, 1. Right? And we are taking the case. So this is your x, and okay, yeah, great. So this is your gamma. Let us make it gamma, and this is gamma dashed. This is sigma. This is sigma dashed. So this is from x0, this is to x1, and this is x2. Okay. So what we are doing here? So we are taking this part. This part will be occupied by this one. Okay. So this is your f. Okay. And this part will be occupied by this one. Okay. So that means, yeah, correct. So therefore, actually you are constructing a map H. This is G. That from 0 to half. So you are taking that f, and from half to 1 you are taking that g. That means h of s comma t is nothing but this f 2s comma t for all s belongs to 0 comma half, and t is in I. And for the other part it is g 2s minus 1 t. So for all s from half to 1. Great. So what we're looking at, so this so this says that, so therefore from these two, so from these paths, so if this gamma and sigma will constitute capital gamma, sorry, and if gamma dash and sigma dash will constitute gamma, sorry, gamma dashed, then these two paths are path homotopy, right? So in view of this, so this suggests us to define some operation on paths which are satisfying that property that the end point of gamma should be the starting point of the next path, right? So that means, so we define gamma star sigma as capital gamma, right? So this is called concatenation of paths. And this operation, so will be well defined on a class of paths. That means, so if we consider this class of gamma, that means we are taking all gamma dashed which are path homotopy to gamma, right? Having same terminal points, right? Great. So if you consider this class, and the class of sigma, then we define the operation on these two path homotopy classes. So it is defined to be the path homotopy class of gamma star sigma, and this is a well-defined operation. Okay, on path homotopy classes in X. Yeah, in X. Great. Okay. So I think I should stop here because it is now 1.5 hours. So I can continue tomorrow. Uh, from the from 9 a.m. Central Time, right? So I think I should stop here. Any questions? So tomorrow I will define covering spaces and covering maps, okay, and also fundamental groups. Yeah. So if you have any questions, then you can write it down in the chat or in the Discord channel chat box also. So if there is no question, then may I leave?